Hello everyone, myself Purva Joshi, Assistant Professor at LJ Institute of Engineering and Technology. Today we are going to study few more topics of sequence and series. So let's begin with the first topic, that is P series test. This P series 1 upon n raised to P. This can be written as 1 upon 1 raised to P plus 1 upon 2 raised to P plus 1 upon 3 raised to P and so on, is convergent if P greater than 1 and divergent if P less or equal to 1. So for example, we have series 1 upon n cube, right? So here you can see P is equal to 3, which is greater than 1, right? So this series is convergent by P series test. Suppose we have a series 1 upon n. Okay, now here P is equal to 1, right? So we can say that this series 1 upon n is divergent by P series test. Now let's study its proof. So consider un is equal to 1 upon n raised to p, and this we will consider as f of n. Now we will apply Cauchy's integral test. Okay, so firstly we will write f of x, that is 1 upon x raised to p. Okay, now this function f of x is continuous, decreasing and positive in the interval 1 to infinite, right? So we can find integration 1 to infinite fx dx, that is integration 1 to infinite fx is 1 upon x raised to p. So just substitute fx. Okay, now this is an improper integral. Okay, so firstly we will write it in the form of limit. So limit m tends to infinite integration 1 to m 1 upon x raised to p dx. Okay, now this we will write as x raised to minus p and we will integrate it. So you will get limit m tends to infinite x raised to minus p plus 1 upon minus p plus 1 and limit is 1 to m. Okay, now apply the limit. So you will get limit m tends to infinite, first upper limit, so you will get m raised to 1 minus p upon 1 minus p minus lower limit, that is 1 upon 1 minus p for p greater than 1, right? So suppose you will take p is equal to 2. Okay, so this limit m tends to infinite m raised to 1 minus p. This limit will become limit m tends to infinite m raised to, in place of p we will substitute 2. So you will get minus 1, right? So this will become limit m tends to infinite 1 upon m. Now as m tends to infinite, this limit will tends to 0. Okay, so for p greater than 1, this limit is 0. Okay, so this answer is 0. So what remains is minus 1 upon 1 minus p. Okay, now let's study for p less than 1. Okay, so for example, take p is equal to 0. Okay, and we will find this limit, that is limit m tends to infinite m raised to 1 minus p. In place of p, substitute 0. So you will get limit m tends to infinite m. Now as m tends to infinite, this limit will tends to infinite, right? So this limit will be infinite, so this whole limit will be infinite for p less than 1. Okay, now we will solve for p is equal to 1. So you will get integration 1 to infinite fx dx is equal to integration 1 to infinite 1 upon x. Why? Because in place of p we have substitute 1. Now again this is improper integral, so we will write it in the form of limit. So limit m tends to infinite integration 1 to m 1 upon x dx. Okay, now integrate this, so you will get log x and limit is 1 to m. Apply the limit, so you will get limit m tends to infinite log m minus log 1. Okay, now this will tends to infinite as m tends to infinite. Okay, so for p is equal to 1, the answer of this integration is infinite. Also you can see that for p less than 1, this integration is infinite, and for p greater than 1, this limit is finite. Okay, so the integral 1 to infinite fx dx is finite if p greater than 1 and infinite if p less or equal to 1. So by Cauchy's integral test, we can say that this series is convergent if p greater than 1 and divergent if p less or equal to 1. Okay, now Next topic is direct comparison test. Suppose un and vn are two series of positive terms. Okay, so if series vn is convergent and un is less or equal to vn for all n, then series un is also convergent. Okay, so we are given one condition that un is less or equal to vn for all n. Okay, and this series vn is convergent. So you can say that this series un is convergent by direct comparison test. Okay, next one. If Vn is divergent and un greater or equal to Vn for all n. Okay, so here condition is given in this form, that is un is greater or equal to Vn and this Vn is divergent, right? So you can say that this series un is also divergent by direct comparison test. Okay, now next one is limit form of comparison test. So suppose we have two series, that is series un and series vn, which are a series of positive terms. And if limit n tends to infinite, un upon vn is equal to l. This l should be a finite and non-zero term. Then both the series either converge or diverge together. Right? So if series vn is convergent, then series un is convergent and vice versa. And series vn is divergent, then series un is divergent and vice versa. So here what we will do, firstly we will find this limit n tends to infinite un upon vn is equal to l. This l should be finite and non-zero term. Okay, and then we have to check whether this vn is convergent or not. Right, so if vn is convergent, then un will be convergent, and if vn is divergent, then un will be divergent. Okay, so for comparison test, we have to define some series Vn whose convergence or divergence is known. Okay, next, in mostly cases, we are going to use following test. First one, P series test. Okay, so to check whether the series Vn is convergent or divergent, we will apply these two tests. First one is P series test. Okay, we know this, that the P series converges for P greater than 1 and diverges for P less or equal to 1. Right, and the next one is geometric series. So geometric series is given by series a r raised to n minus 1, where a is not equal to 0. So this series converges if mod r less than 1 and diverges for mod r greater or equals to 1. Okay, so we will use these two series to solve the example. Okay, now next, determine whether the series 2 plus 3 cos n upon n cube converges or diverges. Okay, so here un is given, that is 2 plus 3 cos n upon n cube. Okay, but we know that cos n is less or equal to 1. Okay, now we will multiply it by 3. So you will get 3 cos n less or equal to 3. Now we will add 2 on both the sides. So you will get 2 plus 3 cos n less or equal to 5. Right, now we will divide it by n cube. So you will get 2 plus 3 cos n upon n cube less or equal to 5 upon n cube. Okay, now we will suppose this term as un and this as vn. We are ignoring 5 because it is a number, right? So we can see that this un is less or equal to vn, and from vn you can see that p is equal to 3. So you can say that this series vn is convergent by p series test. Since un is less or equal to vn and this vn is convergent, so we can say by direct comparison test that the series un is convergent. Okay, next, discuss the convergence of series 2n plus 1 upon n plus 1 whole square. Okay, now here un is given, that is 2n plus 1 upon n plus 1 whole square. Now to solve this, we will take the power of n common. So from numerator we have n, so we will take n common, so you will get 2 plus 1 upon n. From denominator we will again take n common, but it will come out as n square, and here we have 1 plus 1 upon n whole square. 1 n will get cancelled, so what remains is this, right? Now we have to suppose vn. So we will suppose vn as 1 upon n from this, right? So vn is 1 upon n. Now we will find the limit, that is limit n tends to infinite un upon vn is equal to, now if you will divide this un upon vn, right? So this 1 upon n will get cancelled. So what will remain is limit n tends to infinite 2 plus 1 upon 1 plus 1 upon n whole square. Now we know that limit n tends to infinite 1 upon n is 0. So these two terms are 0, right? So what remains is 2, which is a finite and non-zero number, right? Now we have to check Vn. Now series Vn is equal to series 1 upon n is a P series with P is equal to 1. Therefore, we can say that the series 1 upon n is divergent by P series test. Okay, so by comparison test, you can say that the series Un is divergent. Next, test the convergence of series 1 upon 1 into 2 into 3 plus 3 upon 2 into 3 into 4 plus 5 upon 3 into 4 into 5 and so on. Okay, now here nth term is not given. Okay, so we have to find the nth term. Now in the numerator you can see the sequence is like this, that is 1, 3, 5. Okay, and we know this formula to find nth term, that is Tn is equal to a plus n minus 1 into d. Okay, now a is 1, so 1 plus n minus 1, difference is 2. Okay, so simplify this, so you will get 1 plus 2n minus 2. So you will get 2n minus 1. So you can write this numerator as the nth term, right? Similarly, for the denominator, first check this term, that is 1, 2, 3. So we have the sequence 1, 2, 3 and so on, right? Now again we have to apply this formula, that is a plus n minus 1 into d. A is 1 plus n minus 1, difference is 1, right? So you will get n. Next, for the term 2, 3, 4 and so on. So again we have to apply this formula, n minus 1 into d. Here a is 1, so 2 plus n minus 1, again difference is 1, right? So simplify this, so you will get n plus 1. So this is our n plus 1. Similarly, if you solve for 3, 4, 5, so you will get n plus 2. Okay, so this is the nth term. Now we will take n common from the numerator, so n into 2 minus 1 upon n. In denominator, this n and this two other n, so it will become n cube, and here we have 1 plus 1 upon n into 1 plus 2 upon n. Okay, 1 n will get cancelled, so what remains is this. Now we will suppose Vn, so Vn is what? 1 upon n square. From this you have to write, okay, Vn is equal to 1 upon n square. Now we will apply the limit. So limit n tends to infinite un upon vn. So if you will take un upon vn, so this 1 upon n square will get cancelled. What remains is this. Now apply the limit. So this 1 upon n will be 0. So what remains is only 2, which is a finite and non-zero number, right? So we will check this series Vn is convergent or not, right? So series Vn is what? 1 upon n square. So this is a P series with P equals to 2, which is greater than 1. So you can say that series 1 upon n square is convergent by P series test. And by limit comparison test, you can say that this series Un is convergent. Okay. Now another example is the convergence of series sine 1 upon n. Okay, so here un is given, that is sine 1 upon n. Okay, so we know the Maclaurin series of sine x, which is x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial and so on. Okay, so we will find the Maclaurin series of sine 1 upon n. So in place of x, we have to write 1 upon n. So you will get 1 upon n minus 1 upon 3 factorial into n cube plus so on. Okay, now we will take this 1 upon n common. So you will get 1 minus 1 upon 3 factorial. 1 n will decrease. So here we have n square. Then here we have n raised to 4 and so on. Okay, now we will suppose Vn. So Vn is 1 upon n and we will apply the limit. So you will get limit n tends to infinite un upon Vn is equal to limit n tends to infinite. This 1 upon n will get cancelled. So what remains is only this term. Now we will apply the limit. So we know limit n tends to infinite 1 upon n is equal to 0. So this all term will goes to 0. So what will remain is 1, which is a finite and non-zero term. So we will check Vn. So series Vn, that is series 1 upon n, is a P series with P is equal to 1. So by P series test, we can say that this series 1 upon n is divergent. Okay, and by limit comparison test we can say that this series un is divergent. Okay, one more example. Test the convergence of a series n from 1 to infinite 1 upon 3 raised to n minus 1. Okay, so here un is given, that is 1 upon 3 raised to n minus 1. Take 3 raised to n common, so you will get 1 upon 3 raised to n into 1 minus 1 upon 3 raised to n, right? Now we will suppose vn as 1 upon 3 raised to n. Okay, and we will apply the limit, so you will get limit n tends to infinite un upon vn equals to limit n tends to infinite. This is our un and vn. This 1 upon 3 raised to n will get cancelled. What will remain is this. Now as n tends to infinite, this limit will goes to 0. So what will remain is 1, which is a finite and non-zero term, right? So we will check whether this vn, that is series 1 upon 3 raised to n, is convergent or not. Now this series is a geometric series, right, with the ratio r is equal to 1 by 3, which is less than 1. Okay, so by geometric series test we can say that this series 1 upon 3 raised to n converges. Okay, so by limit comparison test we can say that the series un, that is 1 upon 3 raised to n minus 1, also converges, right? So in today's session we study P series test firstly, right? So what we have in P series, that is series 1 upon n raised to p. Now this series is convergent for p greater than 1 and divergent for p less or equal to 1. Okay, and next we studied direct comparison test. Okay, so here what we have, first condition, suppose we have un less or equal to vn. Okay, and this series vn is convergent. Okay, so then this series un will also converge. Okay, and another one, that is if we have this condition un greater or equal to vn. Okay, and vn is divergent. So what we have, this series un will also diverge. Okay, and lastly we study limit comparison test. Okay, so in that firstly we have to find this limit n tends to infinite un upon vn. Okay, and its answer should be l, and l should be a finite and non-zero term, right? Then we will check the series vn by either p series test or geometric test. Okay, so if this vn is convergent, then series un is convergent. Okay, and if this vn is divergent, then series un will also diverge. Okay, so I hope you have understood in this session. Thank you for watching.